Okay, now let's look at the second part of this lab, which would look into GUDHI. Okay, so in order to run GUDHI, I'm sure we have installed on top. So now we can run GUDHI. Two parts again. The first part is to compute the simplicity complex. The next package would be GUDHI.representations, where you would look at the landscape example, the diagram, and etc. Okay. Okay. This code I just added. Yeah, this code would exactly extract Vittori Strips's persistence diagram. Okay. Right. Let's look at it. So first part, GUDHI Reeves complex points would be the data point, the two circles data point, and length I put here 2. Here I know the maximum length would be 2. For example, you see it's like from -2 to 2. That will be the maximum length connecting one point to the other, creating simplicity complex. Okay, so I put maximum there 2, right? So depending on the maximum distance between furthest points, right? Okay, and then here for GUDHI, we have to create a so-called simplex tree. Yeah, this is how the data of a simplicity complex is kept in. So dot create simplex tree and maximum dimension. I want homology class 1, H0 and H1. In order to get H0 and H1, sorry, so you put their maximum dimension is 2. Right, and then dot persistence. So now you're extracting the persistence and you're keeping it as dgmx. Now then you can now look at your persistence diagram by using this function GUDHI.plot persistence diagram diagram x. So this diagram would look exactly like the previous diagram that you have produced using Ripsa's method. Yeah, take note, yeah. Victorious Rips in GUDHI is rather slow. Yeah, kind of slower than Ripsa's package. Okay, so if you really want, like, you have like huge data and you want to run, you want to create a Victorious Rips complex, I would suggest you use use Ripsa's scikit-TDS package. All right. So there are other complex or filtration that you can create using GUDHI. The one of it is called alpha complex. If your dimension of the data is low, for example, 2-dimension or 3-dimension, this would be the best geometric realization of your data. So rather than using a literary strips complex, which is the approximation of your geometry, data geometry, you should use alpha complex. Yeah. Again, with the condition that your data is just maximum 3-dimension. If your data is more than 3-dimension, then I would suggest you use RIPSA. Okay, so for alpha complex, again, it's similar. Your input is just data and then create simplex tree, right? And that's all. It is understood that the data is in lower dimension, so you don't need to set any homology class there. And you just run it and you will get your persistence. Yeah, so as you can see, it's slightly different. Yeah, slightly different as compared to your previous persistence Victorious Strips complex. Again, as I said, this would be a better version of your shapes information, yeah, from as compared to Vittori Strips complex. Right, so you have your birth and death pairs. Now you can represent or vectorize it using persistence landscape. Yeah, so for GUDHI's dot representation, landscape, and then the resolution. Yeah, the previous resolution I used was 500 points to represent one long feature vector. So here I just put here 100 points. Again, I'm going to just use until H1. Excuse me, dimension only H1. Yeah, one dimensional hole, BT1. And so you are keeping it as L. So L, again, if you just extract the first element of L, you get to see one long, lengthy vector like this. Lengthy vector is in fact the layers. Yeah, the first layer, the second layer, and the third layer, and the fourth layer, and so on, all connected as one long strip. If you were to look at strip by strip, lambda 1, lambda 2, lambda 3, and so on and so forth, remember the first lambda is from 0 to 100, second lambda is 100 to 200, third lambda is 200, 300, and so on and so forth. So this is how you plot in order to look at by layers. And whereas rather the first one is to look at just one long strip. Okay, so when you run, so you get to see the layers. The first layer is in blue, second layer is in orange, third layer is in green, and so on and so forth. Okay. You can also represent it, as I said, in the form of persistence image. Yeah, so it's a bit tricky to tell you roughly. This is the resolution. Yeah, this is the resolution, and this is a weight. Yeah, your weight is based on the distance, the y distance actually. Yeah, the death pass, and then the range from what to what, 0 to 0 0.4. Yeah, basically 0 to 0 0.04. You're extracting from 0 0.04, right? And again, that this is your x-axis, and this is your y-axis. You're creating like box, and then your resolution, the x-axis resolution, and of course, again, you're just extracting homology class dimension 1. Okay, so if you run it, then you get to see this is persistent image, right? So I'm going to look at the persistent image, which is just reshaping it 100 by 100. This here pi would be a long flattened array. Rather here it's like 100 by 100. So you get to see the persistent image in this form. Yeah, right. This is another way, yet another way of vectorizing a persistence diagram. So that would be the end of the second part. Next would be using GUDHI's persistence landscape and also classification.